Hello friends, welcome back to our channel Physics for You, and in this video we are going to learn about the Bernoulli's theorem. Okay, so this is a Swiss scientist Daniel Bernoulli who has given this theorem, or we can say the principle, and by which we can talk about the energy of liquid flowing through a tube. Moreover, yes, if the liquid is flowing through any tube, that flow we have to consider, or he has considered, as a streamline flow. That means the liquid has to follow the streamline flow. Yes, so already we know what is streamline flow, what is laminar flow, right? Streamline or laminar flow, and what is turbulent flow. We have a separate video on this concept. If you want, I will post the link of that video in the description box of this video, so you can watch first of all what is streamline flow, and then you can have better understanding of this theorem. Okay, right, now come to this point where what this Bernoulli states. So first of all, let us see the statement of this theorem. This states that the total energy per unit mass of a liquid flowing from one point to another point without any friction remains constant throughout the displacement. That means what he said, as I have drawn a diagram here. So let us consider we have a tube AB as shown in the diagram, and it is of different cross sectional area at two ends, right? So at the end A we have little bit smaller cross sectional area as compared to at the end B. Okay, so if the liquid is flowing in this way from point A to B, okay, so this is actually the direction of flow of liquid, and yes, obviously this flow is a streamline flow. And when we are talking about in any point, at any point in between, so if I am talking about this is the point of consideration, so at this point what this theorem said, the total energy per unit mass, at this point of the liquid remains constant. Okay, this is what simple meaning of the Bernoulli's theorem or Bernoulli's principle. Okay, so obviously this particular theorem ignored the friction. If you see one of the particular line here, without any friction. So obviously if there is no friction, maybe this will be the ideal case, but ideally we have ignored the friction of that liquid with the surface of tube. So just ignore that. So without that friction, so we will consider the liquid is flowing through the tube with the laminar mode, with streamline mode, and if we want to find the energy at any different point, if we see the total energy of the liquid, then that total energy remains constant, whether it is at point A or point B or in between, middle point also, the total energy must remains constant, or it is remains constant. That is what the Bernoulli's theorem. Okay, so yes, this is what simply the theorem. We have to prove it. That is again what we will see in this particular video. Okay, so for this purpose, let us understand what exactly the total energy means. Whatever the Bernoulli said, it is about total energy, not one particular energy. So generally we know the total energy, we are simply sum of the kinetic energy and potential energy, but here one more energy is, that is the pressure energy. We have the liquid flow through that tube, and that liquid, yes, obviously does exert some pressure on the tube. So this pressure energy has to be counted in this particular case, not only the potential energy and kinetic energy. Yes, as usual we have kinetic energy, potential energy, and the pressure energy. So therefore we have the total energy means it is actually the pressure energy plus kinetic energy plus potential energy, and total energy is constant. That means the sum of these three energies remains constant. So that is, we can write in the form of equation. So total energy per unit mass must be constant, and the total energy, as I can write, per unit mass. So pressure, this first term indicates the pressure energy, this is kinetic energy, and this is potential energy. Obviously here it is per unit mass, therefore this will be you won't find mass in this particular energies. So one by one we will see. This is pressure energy. Okay, this is pressure energy, this is kinetic energy, and this is potential energy. So their sum is constant, so we have written in equation form. So that means actually ultimately this is our target, we have to prove this, right? So pressure energy plus kinetic energy and the potential energy must be constant. So for the proof, again come to this point. So for that, let us consider a streamline flow through a tube as shown in the diagram. So I have shown here one more time the diagram. So initially the pressure is P1, and at the last end it is pressure P2. If we say the initial velocity of the liquid is V1 as it is shown in the diagram, and final velocity is V2. let us consider this point A or end A of the tube is at height h1 from the ground surface, and the point B or end B of the tube is at height h2 from the ground surface. Okay, so this is what we will consider, and yes, the flow through the liquid or flow through the tube we have considered as a streamline flow. And the energy of the liquid consists obviously kinetic energy, potential energy and pressure energy. So one by one we will find energies, and finally we will see how the total energy is going to be constant. So first thing we will see is about kinetic energy. So for the proof, what we are saying, the total energy consists all these three energy: kinetic, potential and pressure energy. Okay, now when we say the kinetic energy, we know it depends upon the velocity and mass. So if we talk about a mass, that means a liquid or the particular fluid of mass m and which is moving with velocity v, then yes, obviously its kinetic energy will be half m v square. Yes, so this v you can write the small v, that is velocity, because we have to use another capital V for the volume. Okay, now therefore this is the kinetic energy. But if we say the kinetic energy per unit volume, then per unit volume means volume is equal to 1. So therefore this mass, so if we say per unit volume, that means density is equal to mass per unit volume. But if this volume is unit, that means mass can be written in terms of density. So this rho will be the density of liquid, and now we can replace that mass here in the kinetic energy with the density. So that will be kinetic energy per unit volume. Okay, that is half rho v square. Again this v is smaller v, that is for velocity. Okay, now if the same kinetic energy, if we see or if we write in terms of the per unit mass means again this mass has to be unit, has to be considered unit. So m is equal to 1, and therefore kinetic energy per unit mass becomes half v square only, half v square, that is kinetic energy per unit mass. Okay, now similarly let us find this is what our target, because what is our Bernoulli's theorem once more, that is the total energy per unit mass. So therefore we have firstly found out kinetic energy per unit mass. Now let us go to the potential energy, again per unit mass. So when we say a mass of liquid is moving or is at height h from the ground surface, so we know if m is the mass and height of that particular fluid is h, then obviously the potential energy can be written as mg into h, right? Mass into acceleration due to gravity into height of that particular body or liquid or anything from the ground surface, right? So mg h. And now this is what potential energy. If we want to find the potential energy per unit volume, again I said per unit volume means rho is, if we write the formula for density mass per unit volume, but this volume is 1, so that indicates rho is equal to m. That means per unit volume we can replace this m by rho density. So therefore potential energy per unit volume, again we can write rho g h. Okay, and again yes, potential energy per unit mass. So per unit mass means mass has to be considered unity. So per unit, sorry, not volume, per unit mass. So per unit mass means again mass is equal to 1. So if we substitute m is equal to 1 in this equation, so what remains? Only the potential energy per unit mass is simply g into h. Okay, this is what our second target was. Here we got kinetic energy per unit mass, here we got potential energy per unit mass. Now let us go to the pressure energy. Third energy is which one? Pressure energy. Okay, now the pressure energy, so maybe this is a little bit new for us. So let us see first of all what pressure energy means. So the pressure energy means whatever may be the energy exerted by the pressure or due to the pressure. So when we say a liquid flows through a pipe, then the force exerted by the liquid is, we know the force is nothing but pressure into area. Yes or no? Force is equal to pressure into area. So simply this simple formula we have used here. If we talk about the force at point A, so let us consider initial area is A. Actually there in the diagram we have shown the capital A, so make it correct, capital A1. So capital A1 is the area and P1 is the pressure. So pressure into area we can call it as force. So A1 is area of cross section at point A, capital A, initial end of the tube, we can say. And if we say if that I will just rewrite this, or I can have the diagram once more time. This is A1, right, point A and B, A and B. This end we denote B, but the area of cross section at second end is A2, and the pressure is P1 at initial end and P2 at second end. V1 is the velocity, right, and V2 is the velocity at other end, we can write. So this is at height H2, and this is from height ground, it is H1. Okay. So if V1 is the velocity initially, small v1, and t is the distance within the time, then we can find exactly what will be the displacement of the liquid through within that particular time, or we can say the distance traveled by the liquid in that particular time. So we know distance is nothing but simply velocity into time. This is what simple definition we have used. Velocity is equal to distance upon time. Velocity is equal to distance upon time. So what will be the distance? Distance is nothing but velocity into time. So this is what the distance traveled by that particular fluid and within the time t with velocity v1. Now if we know the force and this distance, or we can right now we can say it as displacement, and then we can find the work done. So work done is simply force into displacement. Okay. So how much is the force? Force we know it is here F into A1, this one, or sorry, P into A1, and into V1 T. V1 T is what? Displacement. So force into displacement. Now again we can write this as little bit in different manner. Pressure I will write aside, and let us write this area into volume into time into one particular bracket. So what it indicates? It indicates the volume of liquid. Volume of liquid. What that area into velocity into time. So that indicates how much is volume flowing through that particular point at that time t. That will be the volume of liquid. So simply we can write work done is nothing but pressure into volume. Now this is capital V, it represents the volume. So this small v represents the velocity. Okay. Now once you got the pressure into volume, that will be the work done. So that work done is nothing but the pressure energy, right? Because that work done has done by the pressure. Only because of the pressure, the fluid or that liquid acquires some velocity and it moves from one point to other point. Therefore, we can say that work done is nothing but the pressure energy. So therefore, pressure energy is nothing but whatever may be the work done by the liquid due to or under the influence of that pressure, and therefore pressure energy is nothing but P1, as it is this P1 into volume V. Okay, or we can rewrite as volume is nothing but, again volume is nothing but what? Density, or we can say rho is equal to mass upon volume. So volume will be here mass upon density if we take this volume to this side and rho to that side. So therefore instead of volume we can rewrite P1 as it is, that is pressure, mass divided by density of the liquid. That is again the another form of the pressure energy. Okay. Now this is simply pressure energy, but we want per unit mass. So let us write below pressure energy per unit mass. So per unit mass means again this mass has to be considered unity, and therefore pressure energy per unit mass can be written as P1 divided by rho simply. Okay. So this is what our third target. Initially we want kinetic energy, yes, we got that. Then potential energy per unit mass, obviously both, and lastly the pressure energy per unit mass, and it is pressure divided by the density. Okay. Now so let us take all these energies in one particular equation form, or we will just rename them again. So what we get, we can recall from above derivation. Kinetic energy at end A we got, again I will draw the diagram here. So this is end A and this is end B. Okay. So at this point we got at point A, what is kinetic energy? Half m v1 square. Okay. Now simply kinetic energy, not per unit mass. And similarly the potential energy at point A we got mg h1, because this height is h1 and this height is h2 from the ground. Okay. Now similarly the pressure energy we got the pressure energy, that is P1 m into, or P1 m divided by rho, or m P1 divided by rho. So these all are the three energies we have at point A. Initially when liquid enters into the tube, we have these three energies, and that the sum of those three energies is nothing but the total energy. So we can say whatever liquid which is now entering into the tube at point A, it possesses these three energies, and therefore the total energy of that liquid at that point will be the sum of these equation 1, 2 and 3, that is kinetic energy, pressure energy and potential energy. Okay. Now, so let us write the total energy. So therefore total energy at point A will be first kinetic energy half mv1 square plus potential energy mgh1 plus m into p1 divided by rho, that will be the total energy at point A. Okay. Now similarly, instead of doing all these things at point B, we can write similarly to the point B. So at point B, simply the difference is what? Here instead of velocity v1, here velocity is v1, but here velocity is v2. Here area of cross section is A2, and here pressure is P2, here pressure is P1, area of cross section is A1. So therefore we can write similarly total energy at point B, that means when the liquid leaves the tube. So that is half m, instead of v1 it is v2 square, then plus mgh2, height is changed, that is why we have to write the change in potential energy gh2 plus m into p2 divided by rho. Again pressure changes, therefore the pressure energy also changes. So these two are the total energies at point A and at point B, that means at initial end of the tube, right, and at the final end of the tube. Okay. But we have one interesting fact, that whatever may be the volume leaving to this particular, or sorry, whatever volume enters at point A is exactly equal to the volume collected at point B, or volume of liquid leaves at point B. That means volume is remains same at point A and B, and that means we can write like this: the volume of liquid entering into the tube at point A, obviously we have to take in the similar time period. So if we are entering the volume at point A in time t, then whatever may be the volume collected at the point B, or volume of liquid leaves point B in the same time is always same, and therefore whatever may be the total energy at point A and whatever may be the total energy at point B must be same, because volume is same, that means ultimately density is same and the mass is same, and whatever may be all these things remains constant, and therefore we can finally write from equation 4 and 5. So what is 4? 4 represents total energy at point A, and fifth equation represents the total energy at point B. So volume same at point A and B within the same time, and therefore we can write from equation 4 and 5 as first fourth equation I have written here, half mv1 square plus mgh1 plus mp1 divided by rho is equal to, similarly the second, that is at point B, half mv2 square plus mgh2 plus mp2 divided by rho, and yes, both are same means whatever may be the total energy, it is constant. So this indicates what? This indicates total energy at point A, this indicates total energy at point B. So obviously both are same means whatever may be the total energy, that remains constant. Now this is what total energy, but we want what Bernoulli's theorem says, total energy per unit mass, and therefore in general we can write per unit mass means if we divide this by mass, then what will be half v1 square, or if we want we can write one more step here, half v1 square plus again gh1 plus p1 by rho is equal to half v2 square plus gh2 plus p2 divided by rho, and that is equal to constant. So in general we can write, instead of v1, h1 and p1, in general we can write the total energy per unit mass will be half v now, not v1 v2, because we are getting the similar value. So half v square plus gh plus pressure divided by density, and that represents the total energy per unit mass. Here I have written Te divided by m, means total energy per unit mass is equal to constant. And yes, this is what the Bernoulli statement, the total energy per unit mass of a liquid flowing through a tube without friction is constant. Yes, this is actually our Bernoulli's theorem. This is now in mathematical form we can say, And if you remember, initially also we have written this statement, so there I didn't explain a little bit more, but what is this? Now you have clear idea how this p by rho gets, how this gh, and how this half v square. So this is what our Bernoulli's theorem. Okay, this says simply total energy per unit mass of a liquid flowing through a tube without friction remains constant at any point. Okay, at any point, right? Yes, this is all about the Bernoulli's theorem, its statement and the proof. So we have proved the statement, and yes, now we can say hence proved. Okay, so yes, this is all about this particular video. Let us stop here. We will meet in the next video with a new concept. Till then, if you feel this is value addition to your knowledge, then like this video. For more such videos, subscribe to our channel, and yes, press the bell icon so that you will get the notifications of our all future videos, right? So thank you friends for watching this video. We'll meet in the next video. Till then, take care and keep learning, keep watching. Thank you.